Okay, so today we are starting to move into the second half of our trigonometry unit. So the first half of the trigonometry unit, we were looking at trigonometry in right-angled triangles. And so this is really familiar from year 9. You learn about SOHCAHTOA, you apply SOHCAHTOA to problems where there are right-angled triangles to find angles and side lengths. Okay. Now what we want to actually do is take a step back to the beginning of trigonometry. Okay, so when you learn about sine, cosine and tangent in year 9 and also at the start of this topic when I introduced them again to you this year, we sort of learn by exploration that when for any right-angled triangle with the same angle, so for any right-angled triangle with a 20-degree angle, for example, when we take the opposite side and divide it by the hypotenuse, we get the same value, regardless of the size of the triangle. Okay, and we learn that we get these sort of constant ratios that are connected to the angle. This is all connected to similar triangles as well, which we haven't reviewed this year, but hopefully you might remember from last year, where if the triangles have the same angles, all the side lengths are in the same proportion. That's essentially what trigonometry is about. So we established these ideas that sine of the angle is opposite divided by hypotenuse, and cosine of the angle is adjacent divided by hypotenuse, and tan of the angle is opposite divided by adjacent. Really just through looking at patterns and observing what happens. But actually, we need to really take a big step back to come back to the actual definitions of what sine and cosine are and where they come from. And we're going to actually do that today. We're going to skip tan for today because it's a bit different and it's a bit more complicated. We'll leave tan until next year. And you'll look at trigonometry a lot more from this perspective through years 11 and 12. Okay, in year 11 and 12 in maths methods, the trigonometry is not at all really about right-angled triangles. It is all about the unit circle. Okay, and that's what we want to begin to look at today, just a very basic introduction. So we want to go back to this unit circle. So the unit circle is a circle with its centre at the origin and a radius of 1. Okay, so if we draw a circle on an axis so that it has its centre at the origin, okay, and the radius is 1, which would mean that this is the point 1, 0, that would mean this is the point 0, 1, it would mean this is the point negative 1, 0, and this is the point 0, negative 1. So that's our unit circle. Everything about trigonometry comes from here. It's actually not about triangles at all, it's about circles, which is an interesting shift when you begin by learning about it being all to do with triangles. So what I've got here is the first quadrant of that unit circle. So the unit circle I've got drawn here on the right is divided into 4 quadrants. Okay, so we have quadrant number 1, is the top right. That's where the x coordinates are positive and the y coordinates are positive. That's where we start from. And then in the unit circle, as we move around it, we move in an anti-clockwise direction. So this is quadrant 2. Down here where both the x and y coordinates are negative is quadrant 3. And over on the right where the x coordinates are positive but the y coordinates are negative is quadrant 4. Okay, so we're just going to start in quadrant 1, and for this year we're only going to focus on quadrant 1 and extending that out to quadrant 2. We won't worry about the other 2 quadrants yet, but again next year being able to think about the full circle and what might be going on is really where the trigonometry starts to head. Okay, so this is where we define sine and cosine. Okay, at some point someone has to say this is what sine is. Okay, what we know, we've learnt sine is opposite divided by hypotenuse. Now that's not how sine is defined. That's a result of the definition of sine and cos that allows us to, that means that it's useful in right angled triangles. Okay, but the definition of sine and cosine are listed here. So if we have a point P on the unit circle such that the line OP, so that blue line, makes an angle of theta with the x-axis, then cos of theta, cosine of theta, is the x-coordinate of that point, and sine of theta is the y-coordinate of that point. That is the definition of sine and cosine. They're all to do with the coordinates of points on the circumference of the unit circle. Okay, so when we're in the unit circle, when we talk about angles, we always measure angles from the positive x-axis. I'm just drawing everything top right in a red pen, from the positive x-axis in an anti-clockwise direction. So when we talk about an angle of, when we talk about an angle of, 50 degrees in the unit circle, we're talking about starting at the positive x-axis and travelling in an anti-clockwise direction for 50 degrees. Okay, that would be the position of 50 degrees in the unit circle. If we were to talk about, sorry, I should have drawn a bigger circle so I could erase. If we were talking about, sorry, let me, I'll just do a big one. If we were talking about an angle of 120 degrees, we'd be going right around here into the second quadrant. Okay, we could talk about an angle of 300 degrees, which would be right around here in the fourth quadrant. Okay, and these definitions apply in all the four quadrants, but let's just stick for the first quadrant for now. Okay, so that means that the coordinates of this point, the x-coordinate of this point is the cosine of theta, and the y-coordinate of this point is the sine of theta. That's the definition of sine and cosine. Tan theta also has a definition in the unit circle, but it's a bit more complicated, and we're going to leave that until next year. We'll just focus on sine and cos in the unit circle. Okay, so this definition should enable us to state the coordinates of the point P in the diagram below. Okay, so here I've got point P is now at an angle of 50 degrees. So I know that the x-coordinate of this point should be the cosine of that angle, cos of 50 degrees. And the y-coordinate of that point should be the sine of that angle. And so I can get my coordinates to two decimal places, because I can work out that cos of 50 is 0.64, and I can work out that sine of 50 is 0.77. So the coordinates of this point are 0.64 and 0.77. Okay? And that makes sense. That fits with the diagram. The y-coordinate is about 0.77, nearly 0.8. Yep, that seems to fit. And this is 0.64, so a bit more than half. Yep, great. Okay. So now that we've established the definition of sine and cosine in the unit circles, we've taken a step back from our right-angled triangles and actually looked at where do sine and cosine start from, we can now consider how that then relates to the right-angled triangles. How do we bring that initial definition to what we already know about sine and cosine in right-angled triangles? So let's have a think about this blue triangle here. I can take out of the unit circle. Okay, so if I have this triangle in the unit circle here, we're going to have a right-angled triangle with an angle of theta in it. Then if the x-coordinate is cos theta, that means that's this distance here. That distance is cos of theta, okay? And if the y-coordinate of that point is sine of theta, that means that vertical distance there is sine of theta. So we can draw this triangle here, this blue triangle, comes out of that definition in the unit circle, okay? And so what we now use when we use SOHCAHTOA is we use the whole ideas of similar triangles. Every single right-angled triangle with an angle of theta is similar to the triangle above. Okay, so similar triangles have the same angles. So if you've got a right angle and this angle also the same, then the third angle has to also be the same as well. So you've got the same angles, and so therefore the triangles are similar. Now when we have similar triangles, all of the side lengths are in the same proportion. So if you take this side length and divide it by this side length, it's the same as you taking this side length and dividing it by this side length. Okay. You can also use other proportions. This sine theta divided by 3 is the same as 1 divided by 8. Okay. 8 divided by 1 is the same as 3 divided by sine theta. 1 divided by sine theta is the same as 8 divided by 3. Okay. But we want to think about what's helpful to us here. So if we think about sine theta divided by 1, sine theta divided by 1 is the same as the equivalent ratio in this other similar triangle, which is 3 centimetres divided by 8 centimetres. And actually what we've got here is what we've already been using, is that sine of theta is 3 divided by 8, which is the opposite divided by the hypotenuse, and we already know what's going on there. Okay. Similarly, if we had this example here then, so 20 degrees, so that means that there would be, in the unit circle, think about the unit circle. Might just draw the first quadrant of the unit circle, okay, just so we can see more clearly what we're dealing with here. Okay, and then if we have a 20-degree angle in the unit circle, what we have then is a triangle that's similar to this triangle in the example. Now we know from our definitions of sine and cosine that the x-coordinate of this point is cos of 20 degrees and the y-coordinate of this point is sine of 20 degrees. Okay, that means this horizontal distance is cos of 20 degrees. That means that this vertical distance is sine of 20 degrees. It's a unit circle, so the radius is 1, so that makes that 1. And so we've got this red triangle here, which is similar to the black triangle. So again, we can use what we know about similarity and ratio, okay? We know that sine of 20 degrees divided by 1 is the same as 5 divided by x. Sine of 20 degrees divided by 1 is the same as 5 over x. So sine of 20 is 5 on x, and then we could solve that for x. Okay, so it's exactly what we already know. Okay, if I go back up to this triangle here, if we now think about any triangle similar to this one, so I'll draw a smaller one perhaps. Okay, also with the same angle in the same position. We know this is the opposite side, we know this is the adjacent side, and we know that this is the hypotenuse. And so our three trig ratios come from this triangle in the unit circle. Well, not tan yet, we'll talk about tan, but they come from this triangle in the unit circle and the ideas of similar triangles. Okay, so if we look at these two similar triangles here, we can say that sine of theta divided by 1, so this divided by this, is the same as the opposite side length over the hypotenuse in another triangle with the same angle. So we get sine theta equals opposite over hypotenuse. Okay. Equally, if we look at cos theta divided by 1, it's the same as adjacent divided by hypotenuse. And this is where our SOHCAHTOA ideas come from. Now tan theta is in fact, you're going to get tan theta by doing sine theta divided by cos theta, which brings up a whole new relationship that we don't really need to worry about for now. So I'll just leave it with sine and cos for now, okay? But what I'm trying to be clear about here is that what I'm telling you now about sine and cos isn't in any way counteracting what you already know. It's just taking a big step backwards to that original definition, and now we're seeing how why sine theta equals opposite divided by hypotenuse, given this original definition, and why cos theta equals adjacent over hypotenuse. Okay, I'm not saying that you are going to draw a unit circle to solve problems in right-angled triangles. You're not going to draw a unit circle. It doesn't. What I'm saying is it doesn't change that we understand SOHCAHTOA, and we can still use SOHCAHTOA as we have been all the time. But I'm taking a step back to try and show you how does SOHCAHTOA come about, okay? Also, this is, as I said, really important going into next year, and there's one or two important things that are going to be relevant as we move through the rest of our trigonometry unit as well. Okay, so now that we have our proper unit circle definition for sine and cosine, cosine being the x-coordinate of a point on the unit circumference of the unit circle, and sine theta being the y-coordinate of the point on the circumference of the unit circle, then we can start to move around from the first quadrant in the unit circle around into the second quadrant, where the angles are between 90 degrees and 180 degrees. Okay, so we're now looking at moving past the 90-degree point, so this angle theta is now an obtuse angle. Okay, so we want to be able to start to, because the rest of this topic is going to be able to look at, looking at how we might use trigonometry in non-right-angled triangles, where it's possible we could have angles that are bigger than 90 degrees. So this is where this becomes relevant. Okay, so now what happens is when we move around into the second quadrant is that we get some symmetry that becomes relevant. So this is a circle. Okay, so there's lots of symmetry in a circle. It's a very symmetrical shape. And we can use that in our trigonometry. So it's clear that between 0 degrees and 180 degrees, there'll be two different angles that have the same sine value. Okay, so if sine theta is if it's the y-coordinate of the point, that means that's that value there. There'll be another point over here which has exactly the same sine value. Okay, so this angle all the way around here and this angle here have the same sine value. So sine of alpha would be the same as sine of theta. Okay, so we want to think a bit about that symmetry. Alright, so I'm going to keep erasing here so I can just use this one diagram. So we want to complete the following statements. So we want to think about sine of 30 degrees. Alright, so let's roughly draw in where 30 degrees would be. Okay, so let's say about there. Okay, so sine of 30 degrees is the y coordinate of this point. Okay, which means y coordinate of this point, we're talking about this point over here. Okay, so sine of 30 degrees is that y value there. So that means there'll be another point on the unit circle, circumference of the unit circle, with that same y coordinate. This point over here will also have a y coordinate that is equal to sine of 30 degrees. Okay, so let's think about what that angle is. All right, let me change my pen color now. So now we're thinking about, okay, well, what's that angle all the way around there? Okay, now obviously it's symmetric, so this angle in here would be 30 degrees, which means that that green angle is going to be 180 minus 30 degrees, so 150 degrees. So we find that sine of 30 degrees is the same as sine of 150 degrees. Those two angles in the unit circle would have the same y value. Okay, let's have a think about another one. Let's see if we can delete that all at once a bit more efficiently. Okay, let's go again. So let's start with sine of 52 degrees. Okay, 52, 45 is halfway, so a bit more than that. Let's say we're up here. Okay, so there's 52 degrees. Sine of 52 degrees is the y coordinate of this point. And so there'll be another point somewhere over here in the second quadrant with the same y coordinate. Okay, and the question is, what angle is this in the unit circle? Remembering that angles are measured anti-clockwise from the positive x-axis. So we're looking for that angle around there. So again, we've got symmetry. If this angle here is 52 degrees, in order for those 2 points to be a mirror image over the y-axis, this angle over here also has to be 52 degrees. And so therefore, this red angle is 180 minus 52 degrees, which is 128 degrees. Okay, and so sine of 52 degrees is equal to sine of 128 degrees. And you can check these. Let's go to the CAS. If I type in, let's check them both. Sine of sine of 30 degrees first, it's half, and sine of 150 degrees is also half. Okay, let's try the other two. Sine of 52 degrees. Sorry, I didn't press, don't let that confuse you. I meant to press enter, sorry, control enter. So sine of 52 degrees is 0.788. Sine of 128 degrees, control enter, is also 0.788. Those two angles in the unit circle have the same y value and hence have the same y coordinate, and hence they have the same sine value. Okay, let's think about another one. Let me erase that. Okay, so this time we want to think about sine of 100 degrees. Okay, so 100 degrees is in the second quadrant. Okay, so 90 degrees plus another 10. So let's say maybe up here somewhere. Alright, so let's say that's 100 degrees. So that means the y coordinate of this point is sine of 100 degrees. So that is this value up here. It would be, if we think about what's happening in the unit circle, it would be something pretty close to 1. In fact, let's have a look. Sine of 100, yeah, 0.98. Okay. Alright, so there's going to be somewhere over in the first quadrant which has the same sine value. Okay, now you can use a few different bits of logic here. Okay, you can think about the fact that it'll be, in order for it to be symmetric, it has to be 100 degrees back from that way. You could think about the fact that this has to be 10 either side of here for them to be in the same position. Okay, either way, we know that that angle there, the position in the unit circle, always measured anti-clockwise from the positive x-axis, is going to be 80 degrees. Okay, and so therefore sine of 100 degrees is the same as sine of 80 degrees. Okay, so what do we notice about the two angles in the brackets? In all cases, they add up to 180 degrees. So sine of x degrees will have to be equal to sine of 180 minus x degrees as a general rule. I don't want you to worry about the general rule. I want you to think about the symmetry of what's happening. Let's think about cos now as well. Okay, let's just clear our unit circle again. Okay, so if we think about cos, so cos of 150 degrees. All right, let's have a look at where that is. So cos of 150 degrees, maybe sort of around here somewhere. Okay, cos being the x-coordinate. Okay, so cos of 150 degrees, sorry, is the x-coordinate at this point. The y-coordinate will be sine of 150, but we're not interested in it. So that's this value here. That value there is cos 150 degrees. So it should be something negative, shouldn't it? Let's put it in the calculator and see. Cos of 150 degrees, control enter. Yeah, it's negative 0.866. That seems to be marrying with what we're seeing in the circle. So what I want to be able to do is connect that to something happening in the first quadrant. So let's think about the symmetry of that. So this angle all the way around to here is 150 degrees. Okay. Let's think about in the first quadrant, which means that if that's 150 all the way around to there, that's 30 up from there. Okay. So let's draw the same triangle over here in the first quadrant. Oops, sorry, try and get it symmetric. Okay, which would mean that's 30 degrees. So we know that the x-coordinate of this point is cos of 30 degrees. Okay, which means that that point there is cos of 30 degrees. Now everything's nice and symmetric here, so that means there must be a connection between cos of 150 and cos of 30 degrees. And it is that cos of 30 degrees will be a positive value, and cos of 150 degrees will be the same value but negative. So if we type in cos of 30 degrees in our cas, control enter, we should find that it's positive 8.66, which it is. So cos of 150 degrees is the negative of cos of 30 degrees. Okay, cos of 112 degrees, let's have a think about that. So cos of 112 degrees, so I'm going to try that again. So 112 degrees, again, that's more than 90 degrees, so it's around in the second quadrant. Okay, so it's 22 degrees past there, right? So let's sort of maybe go somewhere over here. Okay, so let's say that that's 112 all the way around to there, which means the x-coordinate of this point, cos of 112 degrees. Y-coordinate will be sine, but we're not interested in that right now. Okay, so that means that what we find here, the x-coordinate, that's that value there. That is cos of 112 degrees. Let's put that in our cas and get a rough idea. Oh, sorry. Cos of 112. Negative 0.37. Okay, so I probably could have drawn it a bit further, but not too bad. It's about 0.4. Okay, so this is negative 0.37. Okay. Right, so again, some symmetry in the first quadrant. So there'll be another point symmetrically in the same position in the first quadrant, so that the x-coordinate is positive 0.37. Okay, that's what we want. And that will happen if we've got this symmetry happening. So if it's 112 degrees all the way around to there, that means this angle up to here is 180 minus 112, so that's 68 degrees. And so therefore this green angle to here must be 68 degrees. And therefore the x-coordinate of this is, with this point, is cos of 68 degrees. Y-coordinate don't really care about, it's sine of 68, but it's not what we're interested in. And we know that cos of 68 would be plus 0.37. It would be the positive of cos of, well, it would be the negative of cos of 112. So if we take cos of 112, which is a negative number, multiply it by -1, we're going to get the positive number, okay? So cos of 112 is the negative of cos of 68, okay? Same logic. Let's have a look at one more and then let's generalize it. So again, let's have a look this time at cos of 24 degrees. So this time, 24 degrees is going to be down here somewhere. Okay, so that's 24 degrees. 24 degrees, sorry. So that value there is cos of 24 degrees, the x coordinate of that point. And there will be somewhere else symmetrically opposite this point over here where we've got the x coordinate is the negative of cos of 24 degrees. Okay, and that happens at, now this angle all the way around here, that'll be 180 minus 24, so that's 156 degrees. So we would find the x coordinate of this point is cos of 156 degrees, and that's equal to the negative of cos of 24 degrees. So cos of 24 is equal to the negative of cos of 156 degrees. Okay, so it's the same logic. So if cos of 156 is equal to negative cos of 24, multiplying both sides of that equation by -1, it's the same as saying negative cos of 156 is equal to positive cos of 24. It's the same information. Okay. Alright, so again, let's see if we can generalize. So it's the same as what happened previously. These angles are adding up to 180 degrees. So if cos of x degrees is going to be equal to the negative of cos of 180 minus x degrees. Okay? Alright, so there's some work for you to do on the unit circle here. It comes with a big diagram of the first quadrant, and also there's a semicircle diagram of the first two quadrants of the unit circle. I don't want you to use your CAS, I want you to use your understanding of what sine and cosine are to read off the values using the big accurate diagram that you've got on the worksheet. Hopefully when you open it up that will make sense to you. Okay, good luck.